Warning, the video you're about to watch contains mathematics at the level of college algebra and trigonometry. All material has an assumed prerequisite of both Algebra 1, which is elementary algebra, and Algebra 2, which is intermediate algebra. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video begins our 2-video lecture series on hyperbolas. This is a continuation of conic sections. We've already gone through ellipses, and I generally do not cover parabolas, mainly because, well, I don't find that they occur that often in a calculus class, if at all, as far as the strict definition, the conic section definition involving directrix and whatnot. So instead, I focus on what does occur in a calculus course, which would be ellipses and definitely hyperbolas. So let's start into just a concept of what a hyperbola is. And I kind of assume that you've seen them before, but if not, this video and the next one should really reinforce everything you need to succeed in a college algebra or pre-calculus course. So what you see right here is the standard hyperbola, and there are two versions, actually an infinite number of versions of this, but this one happens to have a major axis that is horizontal. So in other words, if you were to draw a horizontal line right here, you could see that both branches, and that's what we call these little pieces right here, that's a branch and that's a branch. These branches go through and are centered around or reflected around that horizontal axis. Now we'll define a lot of other things as we move forward, but the one thing I don't really define is the word branches, and that just means both parts of a hyperbola. So a hyperbola has two disjoint or disconnected curves. Very, very common that you see that. Also, you should notice a hyperbola is definitely not a function. So that's kind of important as well. You can also have these rotated to where they look like, well, I guess I could draw it out like this, right? That is also kind of a rotated hyperbola. Something to note, and this is something that a lot of people don't quite know. Most people do know that, like with parabolas, for an example, parabolas have a focus. And when an external signal comes in for a parabola, so an external signal comes in, it will reflect off the parabola and target the focus. And that's why when you have let's say, some type of satellite TV or something like that, it's always a paraboloid, some type of parabolic shape, and there is a receiving little object right there, which I'll go ahead and call the receiver, but it's really the focus of that parabola because all signals from the satellite up in space come in, strike the dish, and focus or tend toward the focus, and that's what collects all of that signal. Same thing with, by the way, telescopes. They have parabolic mirrors, so light comes in and then bounces or reflects to that focus, and that focus collects all that light, and then you can actually see an image when that focus image gets sent to your eyepiece. However, in a hyperbola, that external signal that's coming in, if you aim it at the focus of one of these two branches, so let me just go ahead and showcase that. Let's suppose the focus for this branch is right there, equidistant on the other side is also the other focus. If you were to have an external signal coming in aimed directly at that focus, that would be right here. What happens is that this reflects off of, that signal would reflect off of this branch of that hyperbola and be directed toward the focus of the other branch. And that's exactly the property of hyperbolas, is that hyperbolas have the property that external signals targeting one focus will reflect from the branch of the hyperbola corresponding to that focus and be redirected to the other branch's focus. And that is not actually how we deal with them, but that is an exact property, kind of a similar property to what parabolas have, where you have an external signal coming in, and no matter where it strikes the parabola, it will be reflected to the focus. Well, sort of similar property here for hyperbolas. Let's go ahead and take a look at a few examples of hyperbolas in the world around us. One of the most common applications that get described when you're talking about hyperbolas is the ripple effect. When you have a couple stones dropped in a pool or something like that, the waves that emanate, or the concentric waves that emanate from those dropped stones, meet in a hyperbolic intersection. So you can see where these wavelets meet are along a hyperbolic path. If you turn your head slightly, you'd be able to see that. Another place we see hyperbolas is really in light spread. When you have a lamp and some type of light in there, you could see the light spread here is hyperbolic in shape. There are a couple other applications of them, but that's not going to be our concern for this video. We really want to define what a hyperbola is. So the definition of the hyperbola in all of its glory, really. A hyperbola is a set of all points in a plane, the difference of whose distances from two fixed points, called the foci, is constant. Now, before we continue on with the rest of this definition, I just want to showcase what this looks like. This web-based app via intmath.com allows us to really visualize what I mean by the distances between these two random weird looking points and some point on a curve is constant, right? So let's go ahead and talk about this. We have a set of points along this curve. You can see these blue curves here, but I'm just dealing with the upper branch. And the points on this curve satisfy the little relation that the distance between the points, like this point P, and the point B, and the distance between the point P and the point A, that distance is constant. The point B minus the point A, that distance is always 2 in this case. No matter where I drag this point, the distance between point P and point B is minus the distance from point P to point A is going to be a constant of 2. Now, obviously, I could change that if I wanted to, but it would just define a brand new ellipse. And now in this ellipse, again, well, you can see that's kind of having a hard time with that. So let me get this where it's really solid there. Let's see if I can do it here. Well, it's supposed to be constant. It's just having problems because it's using a computer. All right. So, but these distances should be roughly 2.35 or something like that throughout. And so if you take all of the points whose distances between P and B minus the distance between P and A, and you keep that at roughly 2.3, you'll see it branches out or creates these two curves. There you go. All right, so that's what I mean by the distance, the difference between those distances of points being constant. And by the way, those points A and B are called the foci. The center of the hyperbola is the midpoint of the line segment connecting these foci. So here's a picture of a parabola here. We have the center, which is the point. Let me go ahead and maybe get orange on here so I match that color. The center is this point right here, halfway between the two foci. And the foci are these guys right here. This is one focus, that's the other. And the plural of having two focuses would be the foci. So the two foci there, they're equidistant from that center, and the center is halfway between them. That's what I mean by that. And then let's see, the Hyperbolas Vertices are the 2 points of least distance from the center. Now, if you take a look at the, there's a lot of noise in this curve, but if you look at all the possibilities of points along a branch here, right? The one point that's least distant from the center would be this point right here. That has the least distance to the center along that branch. And so that point is called the vertex. Same thing on the other side. The point of least distance to the center is also called the vertex over there. So that's what I mean by that statement. And let's see, the line going through these vertices and the foci and the center is called the major axis. However, Most people will not call that the major axis. Unfortunately, they're going to call the line segment connecting the two vertices the transverse axis. I will often just call it the major axis. You could also see that there's quite a bit of other information on this graph. Right now, I don't want to really zoom in on that. Instead, I just want to talk about the foci, these guys right here, the vertices, and the center. And they all lie along the same line, which I will call the major axis. However, most textbooks will call the line segment connecting the two vertices the transverse axis, although there's no real reason to memorize that. All right, and you can see there are a couple little orange dashed lines. Those are called the asymptotes. We'll talk about that in a moment. Now, you may recall, if you've been watching my video series, I'm not a huge fan of conics. Don't know a lot of people who are. And I also don't write conics down the way that most textbooks write conics down. To me, I do not like that they put a squares and b squares in the denominators. The reason why is because when they do that, they change the lettering based upon which of these two, I'll highlight what I'm talking about, which of these two terms is positive. And I just super dislike the fact that they changed the variables. So instead, I just say the constant that's underneath the x squared term is going to be some constant based upon x squared. So I call that v sub x squared because v stands for the word vertex in my head. So let's go ahead and explain why that's the case. Let's see, the standard form of the equation of hyperbola with center h comma k is either of these two equations. And we'll talk about the difference between the two and when you use one versus the other. The vertices of the hyperbola are v sub x units from the center if the term involving x is positive. So in other words, this term right here, if that term is positive, then the vertex is v sub x units from the center. If on the other hand, the y term is the positive term, then the vertex is located v sub y units from the center. Again, that's if y is positive. So essentially the difference between the hyperbola equation and the equation of the ellipse is that this is no longer right here an addition of two terms, it's a subtraction of two terms. And when you have subtractions, order totally matters. A minus B is completely different than B minus A. And so we do have to be very careful with that. All right, let's see. The major axis, which most people will call the transverse, but I call the major axis, is determined by which of the terms involving the variables x and y is positive. So for example, in this first case, the one at top here, the term involving x is actually positive. The term involving y gets the negative. So the major axis here is horizontal. Horizontal major axis. And likewise, if your term involving y is positive, then the major axis would be vertical. That's how I always have remembered it. And I think that's how most students do remember it. Let's see, what else is in that first paragraph? We're right down here. The foci, that's where that beam of external input tends to, right? That's the focus for the hyperbola in this case. They're c units from the center along the major axis, just like with an ellipse. Okay. However, the difference between an ellipse and a hyperbola is that a hyperbola has its focus outside or further away from the center versus an ellipse. An ellipse has its focus closer to the center. And this is the picture from my ellipse video. You can see we have the center right here and the focus is close to the center, actually closer than the vertex, right? Here's a vertex, here's the focus, here's the center. The focus happens to be between the center and the vertex with an ellipse. However, with a hyperbola, the vertex is between the focus and the center. So the vertex and the focus switch position when it comes to hyperbolas. All right. Because of that, the focus, or the location of focus, that distance is going to be a little bit larger than the distance to the focus for an ellipse. Remember, the formula to find the distance from the center to the focus for an ellipse was c squared is equal to the absolute value of v sub x squared minus v sub y squared. In this case, c squared is going to be the sum of the squares of v sub x and v sub y. V sub x being the distance from the center to the vertex in the x direction, and v sub y being the distance from the center to the vertex in the y direction. If I said that backwards, I didn't mean to. All right. And also note, this right here, another way to remember that, if that's subtraction, this will be a plus. If that was an addition, then that would be a minus. That's how that works. Although it would be in absolute values. Not a big deal. And then finally, the hyperbola has something that the ellipse does not. It has a couple of asymptotes. And the equation for those asymptotes is y minus k is equal to plus or minus v sub y over v sub x times x minus h, where v sub y again is the square root of the denominator of the term involving y, and v sub x is the square root of the denominator of the term involving x. Another cool way to remember this is that this is the equation of a line, and when you have the equation of a line, this piece right here is actually playing the role of the, let me go ahead and just make this somewhat large to erase this quickly. It's playing the role of the slope. And we know slope is rise over run, change in y, over change in x, whoops, or change in x. However, if you look at our formula, y is associated with v sub y, and x is associated with v sub x. So if I were to say change in y over change in x, I might just want to say v sub y over v sub x, and there you go. Magically, it's done. Now, that doesn't give you the proof of it, but that is actually what's going on there. That is why it is v sub y over v sub x. Let's go ahead and prove this theorem, and then we'll go, actually, we'll do nothing else because this video is only meant to introduce you to a hyperbola and then prove this theorem. In the next video, we go through and actually work with hyperbolas. Now, just as in our proof for the equation for the ellipse, we're going to assume that this hyperbola is centered at 0, 0 at the origin. It doesn't have to be, but it just makes the proof a little bit easier. And then at the end, you can apply transformations to include the h and the k. Now remember, by definition, when we build an ellipse, it's a set of all points that the difference of the distances between those points and two fixed points is constant. And those fixed points will be called the foci. So let's go ahead and plot some foci here. We'll say this is foci 1, and here, or focus 1 in that case, because we're just singular focus. And this is focus 2. And I'll grab a random point on this hyperbola. Doesn't matter actually which branch, just grabbing a branch there. And we're saying that the distance between focus 1 and that point, which I'll call x comma y, minus the distance from that point to the focus 2, that should be constant. So that distance should be the same no matter what. And just like we did when we dealt with the ellipse, we're going to say that distance is a constant, but we're going to call that constant 2a for a very special reason, just makes the proof a lot cleaner. So let's go ahead and let the distance between point P, which is this point right here, and F1 minus the distance between point P and F2 be some constant 2a. Now remember, the foci are c units away from the center, and we're centering at 0, 0 just for ease here. So this point right here is c units over, so this focus point right there is going to be at negative c comma 0. The other focus point will be at positive c comma 0. Not a biggie. Now, using the distance formula here, we know that the distance between point P and focus F sub 1 is going to be the difference in their x values, so x minus a negative c being squared, oops, being squared, plus the difference between their y values. Y value of point P minus the y value of the focus f sub 1 squared. And same thing for the other point, the distance between point P, which its x value is going to be x, minus the x value for point f2 is c squared, plus the distance between their y value squared, so y minus 0 being squared. And we're calling that 2a. Now this would be much easier. You've solved radical equations, so we're going to solve this radical equation. We're going to isolate one of the radicals. I'll isolate the radical on the left. That's just much easier to isolate. So that's going to be the square root of x plus c being squared plus y squared is equal to 2a plus the square root of x minus c being squared plus y squared. Now we will square both sides. When you square the left-hand side, the square root disappears, just like when we proved this for the ellipse. On the right-hand side, the square root doesn't actually disappear because you have 2a plus that square root times 2a plus that square root. So that'll be 4a squared plus 4a times that square root. Whoops, that's supposed to be x minus c quantity squared plus y squared, and then plus that square root being squared, so plus x minus c quantity squared plus y squared. Now something magical happens here. You could probably see it, but the y squareds will cancel on both sides, so that's kind of nice. But also, you want to spend some time isolating this radical right here, in fact this term involving a radical right there, because you want to again square both sides. So I'm going to subtract y squared from both sides. I'm also going to subtract x minus c squared from both sides and 4a squared from both sides. The next thing I'm going to do is actually just distribute out or combine terms on this stuff right here. You could either use that as a difference of squares or just multiply things out and combine like terms. I'm going to go ahead this time and multiply things out. Mainly because the last video I used a difference of squares to showcase that you could use that, but I'm not going to do it this time around because I just don't want to. Plus 2cx, let's see, plus but minus c squared. I distributed this negative through, by the way, if you're wondering where I got the plus 2cx, it's because negative times negative becomes positive. And then remember, we still have a minus 4a squared, and that's going to equal 4a times the square root of the quantity x minus c and quantity squared plus y squared. Combining like terms, the x squareds cancel. We get 4cx. Let's see, the c squareds cancel. Minus 4a squared is equal to 4a square root of x minus c, quantity squared, plus y squared. And obviously everything is divisible by 4, so I'll just divide everything by 4 and we get down to that right there. This is kind of beautiful, actually. Now we're just going to square both sides, so you get this cx minus a squared being squared is equal to a squared times the quantity x minus c being squared plus y squared. And you could multiply out that cx minus a squared pretty quickly. That's c squared x squared minus 2a squared cx plus a to the fourth. Now notice we have a squareds everywhere here, right? So you get an a squared times x minus c squared plus a squared y squared. It's just a lot of a squareds. I'll go ahead and distribute things out on the right hand side. I'll keep the left hand side as is, because that might be useful in the long run, who knows. Let's see, on the right hand side, I will get a squared x squared minus 2a squared cx, and then plus a squared c squared, and finally plus a squared y squared. Let's see if anything cancels. Just those two terms right there. Now what I'm going to do is collect everything involving x's and y's to one side, and everything without x's and y's, I'll leave that on the right hand side. It's a nice common trick here. So we'll still have the c squared x squared let's see, I'm going to move an a squared x squared over here. I'll also move the a squared y squared over here. On the right hand side, I'll have the a squared c squared because it was already there. And I'm going to move the a to the fourth over there. So there we go. We've collected everything with x's on x and y's on one side and everything without on the other. And you can also tell I can factor an x squared out of those first two terms, and I have a c squared minus a squared times x squared minus a squared y squared is equal to, and I suppose I could just factor out an a squared here, a squared times c squared minus a squared. Okay, now I'll divide everything by a squared, by this picture basically, a squared times the quantity c squared minus a squared. When you do that, you get x squared over a squared minus y squared over c squared minus a squared is equal to 1. Yay, we're down to that point right there. Now I'm just going to say, well, we didn't actually know what a was. We know what c was, but we didn't know what a was. We're going to go ahead and let a equal v sub x in this case. And we're going to let b, sorry, not b, but v sub y squared equals c squared minus a squared, which, by the way, a, remember, is v sub x. That is, c squared is going to be equal to v sub x squared plus v sub y squared. So far, so good. All I did was move that to the other side. Okay. If you do that, your formula is x squared over v sub x being squared minus y squared over v sub y being squared is equal to 1, where c squared is equal to v sub x squared plus v sub y squared. And if you take a look at our formula way up top, that is exactly what we have for the first part. I'm not going to do it for the second part, but that's what we have without the shifts. So if you ignore these h and k, that's what we have. X squared over v sub x squared minus y squared over v sub y squared is equal to 1. That's what we just have arrived at. And we have the relation that c squared is equal to v sub x squared plus v sub y squared. So that's pretty cool. The asymptotes, you usually require calculus to kind of prove something like that. So we're not going to use that here. But when you start involving shifts, if you want to move a graph left or right so many units, you involve that. If you want to move it up or down so many units, you involve that. And that is a complete proof. So from this point forward, we're just going to go ahead in the next video and use this theorem to go ahead and graph hyperbolas.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way, cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close, don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.